Hello, we're Team 2, and this is our final presentation on the analysis and redesign of a pencil sharpener. The following slides can be found in further detail in our interim report, but we'll go quickly through them, and we'll be going more into detail later. This is our product description, which is a sharpening tool that uses a crank to cut the end of a pencil at a certain angle and collect the shavings. This is the exploded view. Our primary customers is the education sector, and our secondary customers, the industry professionals. This is our FAST diagram. This is our function component mapping matrix. This is our product family design with the primary customer base and the secondary customer base. This is our quad chart. This is the product family design. These are the shared platforms. And these are the assembly sequences.
Here you can see a table showing the manual assembly times for all of the components in the pencil sharpener. Both the blade gear and the crank pictured below had a rather high assembly time at 13 seconds and 6.5 seconds respectively. Both parts were listed as high functionality and high cost items in the quad chart. And it was for these reasons that we decided to redesign these parts for manual assembly. Here you can see the redesigned version of the blade gear. Following DFA 1, we were able to combine the gear and bushing with its separate bushing counterpart to reduce part count. Following DFA 7, we blocked off the end of the gear that should not be inserted onto the blade shaft to reduce assembly errors. And following DFA 10, we also added a chamfer onto what was originally a square hole edge to allow for easier insertion onto the blade shaft. The original assembly time for the blade gear was 13 seconds and has now been reduced to 6.45 seconds. For the crank, following DFA 1, we combined the crank with the crank socket to reduce the number of parts. So now the crank will engage directly onto the pencil slot. Following DFA 6, we were able to give the part 180-degree symmetry by making the hole at the base a through hole and by removing the crank handle attachment point and making that a through hole as well. This did mean we had to redesign the crank handle, and this redesigned handle can be seen with the crank above on the left. Following DFA 10, we included a chamfer onto both edges of the hole that can mate onto the pencil slot to allow for easier alignment and insertion. The original assembly time for the crank and crank socket was 9.93 seconds and has now been reduced to 4.25 seconds. After making these changes to the crank and the blade gear, our assembly efficiency has increased from 45.6% to 52.6%.
Next, we'll take a look at design for automated assembly, where we chose to redesign the body, shaving box, and slot holder assembly, because all three of these fell in the high functionality, with two of them falling in the high cost of the quad. If you take a look at the next slide, we can see the before for this, where we have a $2.18 cost to assemble. And on the following slide, we have the after, where we followed DFA 1 by reducing the part count, removing the slot holder, DFA 6 by increasing part symmetry in the shavings box, DFA 8, we have a bridge to avoid nesting, and DFA 10, where we have features for the easy insertion. None of the functions were affected by the changes in either of our product variant, and our new cost is now $1.51.
Here's the manufacturing process for the new part designs. We use the process selection matrices described in Lecture 6. The two parts we analyzed are the blade gear and the crank. As you can see in the function component mapping matrix, both the blade gear and the crank contribute to torque transmission. Here are each component's critical dimensions. The crank's critical dimension is the distance between the handle and the crank gear, since its length affects the torque transmitted by the user. The distance is 39 millimeters. The blade gear's critical dimension is the diameter of the gear, since it also affects torque transmission. The gear has a diameter of 12 millimeters. On the next slide is the process selection matrix we used to determine the best method for manufacturing the crank. Both machining and injection molding would be acceptable methods. However, we chose injection molding because it would have lower operating costs. On the next slide is the same process with the blade gear, and machining was the only appropriate manufacturing method.
Our redesign also followed DfM guidelines by minimizing wall thickness in the middle of the crank, avoiding the side pole, and integrating a chamfer, which fulfilled DFIM 8. This is the isometric view of our redesign, as well as feedback from DfM Pro, which said that our radius to thickness ratio needed to be improved. This redesign significantly decreased the unit price, decreasing it by 71%.
When we made DFA changes to the blade gear, the main change was to put the bushing and gear together as one part. This saved time in the machine time of features section, since the part did not need to be cut in half anymore to produce the two pieces. Other than that discrepancy, the two manufacturing processes are identical and produce the same output for material cost and non-productive time. Ultimately, this slight change produced a price reduction of 48 cents from $3.52 to $3.04. The post-DFA design of the blade gear can be seen above, and some critical dimensions are given as well. Some changes we made according to the DFM guidelines are DFM C5, avoid long narrow holes, DFM C6, avoid drilling inclined surfaces, and DFM C15, minimize tool changes and setup, which all had a great effect on reducing the cost of manufacturing. Additionally, our part was redesigned well because DfM Pro did not have many suggestions to improve our design. As we see on the left, Hubs estimated the cost of our original part to be a combined $2.74 and the cost of our redesigned part to be $2.28. Although the prices for each cost estimation method do not match perfectly, the difference between the before and after for each method is very similar, which is promising.
Next, we'll take a look at the product service that we'll be offering, which is a rental. This can help reduce the startup costs for any new school or office opening up, as they can get tens of pencil sharpeners for a cheap rental fee instead of the full price. They can easily replace broken pencil sharpeners, and this leads to a positive impact on the environment as we reduce by product sharing, reuse parts that we receive from broken products, and recycle the parts that we cannot. And finally, we have the conclusion. So you can see the DFA manual was a success, as both the crank and the blade gear were reduced by over 5 seconds. The DFA automated was also a success, as we saved 67 cents per unit. And then our DFM was also a success, as we reduced by 39 cents per part and 48 cents per part for the crank and blade gear respectively. Our critiques, two of which have been mentioned, were about the crank, the handle being redesigned, and the uniform wall thickness. And a third critique is that the body becomes more expensive and will now take longer to manufacture from the automated assembly changes. Had we been able to restart this project, I think a greater emphasis would have been placed on the SCMM and defining our functions, as this laid the groundwork for the entire project. Thank you for your time.